Hello, everyone. Mr. Minnick's my name. Math is my game. And today, in Algebra 2, we're going to continue this 6-6. Last week in class, we started this on the side dry erase board. And we talked about the function operations. We talked about adding, subtracting, multiplying, and dividing functions last week. So we're going to continue a discussion of that. And we'll also be talking about the other component of this. So you can kind of think of this lesson in three parts. Adding, subtracting, and multiplying being one part. Dividing being another part. And the other part is a composition of functions. And some of the notation they use, it looks like the word fog. But it's actually not. It's a composition of two functions. It's putting a function into a function. It's taking f of g of x. So that's kind of where we're heading today. The Common Core Content Standards are FBF1B and FBF1C, combined standard functions using arithmetic operations and composing functions. So these are in the Common Core curriculum, and that's why we're looking at this. So the other day ago, we said you can add functions, and I believe that the notation that I used last week was f of x plus g of x, f of x minus g of x, and f of x times g of x. Just to kind of, to be clear, writing f plus g of x means the same thing as f of x plus g of x. So when I give you tonight's homework, if you're confused by the notation, notationally some textbooks will say f plus g of x. Just know that that means the same thing as f of x plus g of x. Same thing with subtracting, multiplying, and even dividing. Okay, and even dividing. So here in this key concept box, they say what I said the other day, talking about the domains of these things, saying that to figure out the domain of the result, that you have to find the domain of each individual function. And when it comes to dividing, that you have to take whatever function is in the denominator, and that function in the denominator is not allowed to equal 0. So really this key concept box isn't saying anything that we haven't already said last week. Okay? It says if you want to find the domains of f plus g, f minus g, and f times g, you got to find the domain of f, find the domain of g, and kind of put those together. If you want to find the domain of the quotient, well, you also have to consider that the denominator, whatever function you put into the denominator, is not allowed to equal 0. So last week we did an example of a sum, a difference, a product, and that was all example 1. Example 2 was an example of doing a quotient. So we're going to go back, we're going to revisit this, we're going to look at another example of those, and then primarily today I'd like to focus on the other idea, that composition of functions. So I hope everybody's ready for the end of the school year. One of these days I got to show you a video on how to finish off the year strong, 7.25 ways to finish off the school year on a quick note. It's a great video. It's awesome. It's very inspirational. Not quite as inspirational as watching the movie Rocky, but inspirational nonetheless. Are there any questions about the notation of anything? About domain? About range? Okay. So, problem number 1, they have f of x as 4x plus 7, and g of x is the square root of x plus x. Those are kind of interesting functions. And they're asking you, what are f plus g, and what are f minus g, and what are their domains? So I'm going to go ahead and cut this out and put this on a clean page, because on this page, all the answers are kind of under a box. That's the way I built this set of notes the first time I did this. So I'll send this out to a new page. And what we saw last week is this first part of it, taking f plus g, that's really easy. All that is substitution. All that is a substitution. F plus g of x, or if we want to write it, f of x plus g of x. However we want to write it, regardless, either way, it's just going to be 4x plus 7 plus the square root of x plus x. Now, if we look at that expression, we should be able to simplify that. We can combine some like terms, can't we? What can we combine? Does the 4x have anything that can combine with it? The x could. So that's going to give us 5x. The 7 really doesn't have anything to combine with that, so 5x plus 7, and then plus the square root of x, right? So that's our best answer for that part of it. That's not bad. The other part, finding f minus g of x, or f of x minus g of x. We're just going to substitute. That's going to be 4x plus 7 minus the quantity of rad x plus x. Probably the most critical part there is using parentheses. Using parentheses around that quantity of the square root of x plus x. So again, we're going to combine like terms. This 4x and this x can go together. 4x minus x is going to give us 3x this time. So that'll be 3x. We still have the plus 7. And then we have minus the square root of x. Then we have minus the square root of x. Then we have minus the square root of x. So that's our best answer for that part of it. And that's pretty easy, pretty straightforward. Just substitute, combine like terms if you can. Right? What's tricky about this is the back end of this. What are their domains? And the thing is, the answer for the domain of this is going to be the exact same as the answer for the other one. So whatever we get for the one, we're going to get the exact same answer for the other one. And to figure that out, we got to know the domains of each function. So if we think about this, the domain of f, that's a line. When we graph that function, it's going to look like this. It's going to be a line. Its domain is not restricted. The domain of f's domain is not restricted. It's all real numbers, negative infinity to infinity. If we think about the function g for a minute, the function g, running out of colors here, this function, it's a square root function, and I know I'm not allowed to put what kind of numbers under square root? Negatives. So my domain here, so g's domain is that I can't have negative x values. I can have 0, but I can't have negative x values. So g's domain is going to go from 0 to infinity. So to answer this question about the domain, I have to join those two things together. There's no restriction, but the one has to be greater than or equal to 0. So when you join all those together, the domain ends up being from 0 to infinity. That's the answer, from 0 to infinity. And we said whatever you get over there is going to be the answer over here too. And just to show you that I wasn't lying about that, if we go to the book, let's see what the book did. Let me unlock this. So they said f of x plus g of x, what did they get? 5x plus rad x plus 7. We got that. Different order, but we got that. The difference, they got 3x minus rad x plus 7. We got that. Different order, but that's okay. Commutative property, we're good. Let's look at the domains. They said the domain of g is x is greater than or equal to 0. So the domain of both f and g, what did they say? The domain of both f plus g and f minus g is a set of numbers common to the domains of both f and g, which is all x greater than or equal to 0. So we're good on both counts. And that's it. Are there any questions about function operations and about their domains? If not, now that was for sums, and that was for a sum and a difference. Let's see what example 2 has. Example 2 has multiplying and dividing. So example 2 here has got multiplying and dividing. So the first thing they want us to find is f times g. So f times g of x, or f of x times g of x. So regardless of what notation we use, that's going to be where we take x squared minus 9 and multiply that by x plus 3. Again, we have quantities. This here is a quantity. This is a quantity. We probably ought to use some parentheses. Probably ought to use the FOIL method. We're going to get x cubed plus 3x squared minus 9x minus 27. So that's our answer for the product. That's not bad. Not bad at all. For the quotient, I really like this example that they used. For the quotient, we're going to have x squared minus 9 over x plus 3. That's what we're going to get for f over g of x. Or, if you want to use this notation, f of x over g of x. Okay? Both of those notations end up, giving us the same result. Anybody remember what we could do to this? What we should do to this to simplify it? This is chapter 8, section 4, factor, right? That numerator is going to factor. This is going to factor into x plus and minus 3. X plus and minus 3. And then this denominator here is still x plus 3. So we can cancel. So our answer for this part of it, ends up looking like x minus 3. That's pretty cool. And again, they ask, what are their domains? What are their domains? So part of this is pretty easy for the domains. If we look at f, f's domain, the function f is this parabola. Parabolas are not restricted. F's domain's all real numbers. If we look at g's domain, g, the function g, it's a line, and we said that there's no restrictions on a line. So g's domain's all real numbers. So the answer to the part about the domain of this, the domain of f times g, when we're talking about the product, the domain of that is going to be all real numbers. So our answer here is going to be all real numbers, negative to positive infinity. Negative to positive infinity. So that's the second part of our answer for that one. Now that's for the product. Does anybody remember what we have to remember when it comes to the dividing? That little caveat, that little thing to watch out for? The little, remember this part, don't forget. Can't go out of state. Well, what about Siri and your friends? And you don't have any friends. When Siri tells you you don't have any friends? When you try to divide by 0. So we're looking at what function we put in the denominator. Here we're putting the function g in the denominator. So g of x, this x plus 3 is not allowed to equal 0. So x is not allowed to equal negative 3. So the domain of this part of it's going to be from negative infinity to negative 3, union negative 3 to infinity. That's what we're looking for in that. X is not allowed to equal negative 3. If we want to see confirmation of that, again, like we did last week, we'll take a look on the calculator. Sometimes using a graphing utility is very handy. I've got this new software here for this calculator. Add calculator page. I'm defining the function f. I said I'm defining the function f at x as x squared minus 9. I'm also defining the function g of x as x plus 3. And then I'm going to insert to my document a graph page, and I'm going to graph the quotient f of x divided by g of x. When I graph it, it's kind of interesting. I see a line. And if you go back to what our answer was, if you go back to here, x minus 3 is a line. So it shouldn't really surprise you what the graph looks like. But there's something on the graph that we don't see that's going on right here. Anybody know what's going on there? There's a removable discontinuity there when x equals -3. If I go menu, trace, graph trace, and I were somehow, some way able to stop when x equals -3, let's see, menu, window, zoom. Let me try zoom. Menu, window, zoom. Let me try zoom decimal. I don't know why my smartboard's not letting me go to the zoom decimal. Let's try it this way. Whoop. 18th time's the charm. Menu, window, zoom, zoom decimal. Come on, work with me. Zoom decimal. There we go. So, menu, trace, graph trace. Let's see what happens. Oh, whoa. You see that when x is -3? The function's undefined. But you really don't see that hole. You've got to kind of know the math of everything, and you got to kind of realize that the denominator can't be 0. Okay. So that gets us up to speed. That's basically a recap of everything we did last week. Any questions so far? Well, what we're getting into next then, you really got to understand F notation. You really got to understand F notation. F notation. Suppose f of x. Suppose f of x. Suppose f of x. Suppose f of x equals 3x minus 10 all over the square root of x. Now, there's something inherently wrong about that. I know you're not supposed to put radicals in the denominator. I know. But I did. But suppose that's what our function f of x looks like. If you really understand f notation, you should be able to go ahead and find f of 2. F of 2. What does that mean, f of 2? Well, we know that f of x is 3x minus 10. F of 2, in a sense, says, rather than f of x, we're taking f of 2. So wherever there's an x, we're going to put a 2 in its place. So instead of 3 times x minus 10 over the square root of x, wherever there's an x, we're going to put a 2. We're going to put a 2 here. We're going to put a 2 here. So that's times 2. That's an x. Does that make sense? Oh, dang it. That last x shouldn't have been an x, though. That last x should be a... That's a 2. Sorry. Oops. So f of 2 is 3 times 2 minus 10 all over rad 2. Does that make sense? F notation? Okay. Let's go ahead and find f of alpha. What's f of alpha going to look like? F of alpha says we're going to put an alpha in place of every x. F of alpha says we're going to put an alpha in place of every x. So we're going to have 3 something minus 10 all over rad something. We're going to have 3 what? 3 what? 3 what? A, or it's a Greek letter alpha, so 3 alpha minus 10 all over the square root of alpha. People all of a sudden, when you start throwing variables in here, they get freaked out. Don't get freaked out. It's the same thing. So let's see if we can find f of x minus 2. See if we can find f of x minus 2. What's this going to look like? Three times the quantity x minus 2. 3 times the quantity x minus 2. So So instead of x minus 2, we're going to replace x. Instead of x, we're going to replace every x with x minus 2. So it's going to be 3 times x minus 2 minus 10 all over the square root of x minus 2. All over the square root of x minus 2. How's everybody doing up to that point? Does that make sense? Try one more. Let's see if we can find f of Kool-Aid Man. See if we can find f of Kool-Aid Man. Everybody loves Kool-Aid Man. F of Kool-Aid Man, what's that going to look like? Three Kool-Aid Man. And then what? Minus 10. All over. All over red Kool-Aid Man. Does that notation make sense so far? Okay, so what we're going to do now, is find f of x. What? You can do that? Yeah, you can do that. To be clear, this is not f of x times f of x. It's not f of x times f of x. It's f of x. Okay? We read this as, this is read as f of x. With f notation, all we're doing is making substitutions. We replace the x with something. So f of x means we're going to have the general structure of f of x, which is 3 times something minus 10 all over the square root of something. But what's going to go in the place of x now is f of x. Well, what is f of x in this instance? What is f of x? Isn't f of x all this? So all that's going to go here and here. So this is going to be 3x minus 10 over the square root of x. And this is going to be 3x minus 10 over the square root of x. What do you think? This is called the composition of functions. This is putting a function into its function, into another function, rather. This specific instance is putting a function into itself. That's something that sometimes you do. More often than not, though, you do this with two different functions. You put one function inside of another. Anybody ever see those China dolls? The nesting dolls? What do they call those? I don't know if they're China dolls. The nesting... The Russian nesting dolls. That's kind of what this is. Well, it's mathematically speaking, I guess. So, suppose f of x equals x plus 2, and g of x equals x squared. Let's see if we can find f of g of x and g of f of x. Let's see if we can do this. So remember, this is essentially nesting something inside the other something. All it really is a substitution. F of g of x, what we're going to do is we're going to replace g of x with what g of x equals. We're replacing g of x with what g of x equals. Well, what's g of x equal? G of x equals x squared. So we're really finding f of x squared. So So we could think of it as this way. It's really f of x squared. So if we think about it that way, we're going back to the function f, and we're going to replace every single x with an x squared. So essentially, we're going to take this x squared and just stick it right into there. So this is going to be x squared plus 2, and that's it. That's our answer. That's it. That's our answer. Does that make sense? The 2 was part of the original function f. Yeah, when I take the x squared and I f it, what I'm doing is I'm just plugging x squared into the function f in place of the x. So the function f has a plus 2 in it. So my answer's going to have a plus 2 in it. So let's see what happens when we take g of f of x. When we go the other way with this g of f of x, we're going to replace this f of x with this x plus 2. So we're taking x plus 2, and we're g'ing it. So we're going to go to the function g and replace x with x plus 2. So here we're going to replace the x with an x plus 2 when we find g of x plus 2. So what's that going to look like? The function g says take whatever you have and square it. Take whatever you have and square it. Well, what do we have? We have x plus 2. We could leave our answer right here like this. If you wanted to expand that out, you could expand it out. But that's it. That's it. All it is substitution. It's not multiplying. It's substitution. From a notation perspective, speaking of notation, f of g of x is the same thing as saying f composed with g of x. Some textbooks use the fog notation. That little dot right here, this dot means composed with. Composed with. That's what that dot means. I didn't learn about this stuff until I was in Calc 1. They didn't teach me this when I was in high school. All right. So let's go ahead and try problem 3. Problem 3 is kind of neat because they don't want g of f of x or f of g of x. They want f of g, or g, in this case, g of f of a specific number. Of a specific number. So they're letting f of x equal x minus 5. They're letting g of x equal x squared, and we're asked to find, they're telling us to find g of f of negative 3. So remember, all this is a substitution essentially from the inside out. We're substituting from the inside out. The first thing we got to do is take negative 3 and f it. Now, I got to watch when I say that. I don't literally mean we're effing negative 3. I mean we're taking negative 3 and we're putting it into the function f in place of the variable x. We're taking negative 3, putting it into the function f in place of x. So this whole first bit of substitution, what we're going to do, it's going to look like this. Instead of x minus 5, it's going to be negative 3 minus 5. Instead of x minus 5, it's negative 3 minus 5. Now, what you've got to remember is we still have to g that. We still have to g that. We're still going to g that. And when I say g that, I mean take that, plug it into the function g in place of x. Let's think about this. What's negative 3 minus 5? Is that negative 8? So this is really asking us for g of negative 8. So that means let's go to the function g, let's plug a negative 8 in and see what we get. So g says take whatever you have and square it. Well, we have negative 8, and square that. What's negative 8 squared? 64, boom. So that should be our answer. The cool thing is, my calculator can do this with numbers for me, not variables. Darth Vader can do this with variables. But your regular TI Inspired can do this with numbers. So let's try this. Into my document, I'm going to insert a new problem. I'm inserting a new problem. And on a calculator page, I'm going to define f of x as what it was. X minus 5. And I'm going to define g of x as what it is. G of x is x squared. And what I was asked to find, I believe, was g of f of negative 3, wasn't it? Check that out. Boom, 64, just like that. You're going to have these on your final exam. You're going to have these on your take-home test. The calculator can do these. I think those are pretty easy to do by hand, but whatever. Any questions about that? Let's go the other way with this. Let's try f of g of negative 3. F of g of negative 3. Now remember, f of x was x minus 5. G of x was x squared. So f of g of negative 3. F of g of negative 3. What I'm going to do is I'm going to go to the function g and I'm going to put negative 3 in. So the function g says square it. Square what? Square negative 3. And then I still have to f that. And again, don't get it twisted. Don't take this the wrong way. When I say I have to f that, it means I'm going to put that into the function f in the place of x. So when I take negative 3 and square negative 3, that's going to be 9. So what I've really got going on here, is I'm taking f of 9. So I'm going to take 9, I'm going to f it. I'm going to put 9 into the function f in place of x. So instead of x minus 5, it's 9 minus 5, which is going to be 4. Okay, should be 4. So on my calculator, I should be able to just punch that in. F of g of negative 3. And there it is, it's 4. Okay. Are there any questions, comments, concerns, short debate so far about this? Yeah. Back to the other page, back to what, to this one? Okay. I'm walking into things. At least I didn't trip and fall. You're probably thinking, man, this is a weird idea. Why on earth, in a math class, would we have to do this? If you think about the way math goes, you could probably answer your own question. We studied Chapter 8 before we studied Chapter 6, right? Because in Chapter 8, you had to know how to deal with dividing polynomials by polynomials and how the domains shook out. And you had to know that for this section. Well, it's the same thing. Everything's sequential. When we get into the next section, we're going to talk about inverse functions. And to prove the functions are inverses, you have to compose them with each other and show that something happens. So, and then the reason we're doing that before Chapter 7 is because when we get to Chapter 7, exponential functions and log functions are inverses of each other. And to show that they're inverses of each other, you have to be able to compose them with each other to show that they're inverses. So anyway, it all ties together. This Chapter 6, 7, and 8 is really kind of a cohesive unit that goes together. So this is kind of cool. They have a practical application of this. They say, you have a coupon for $5 off. I'm going to go ahead and call that f of x. A coupon for $5 off. I'm going to call that f of x. The function f of x then could be thought of as paying full price, but getting $5 back. So x is how much I'm paying. X minus 5 means I'm paying $5 less than that. So that's how I could model this with functions. It says you also get a 10% discount. You also get a 10%, I meant to change colors of the marker. You also get a 10% discount. A 10% discount. Well, 10% discount, I'm going to let that equal g of x. That's going to be g of x. So let's see, I'm not going to be paying full price, I'm going to be paying full price minus 10%. So that would be x minus 0.1x I can write that better than that, though. X minus 0.1x. I guess g of x would be best written as 0.9x, because that's how much I'm paying. I'm paying 90%. This is interesting. It says, how much more would you pay for the large pizza if the cashier applies the coupon first? Let's take some thought. Coupon first. Coupon first. That's either going to be f of g of x or g of f of x. Think about that. We work our way from the inside out. The thing on the inside is what we do first. Doing the coupon first means the coupon would have to be on the inside. So g of f of x, g of f of x would mean the coupon is applied first. Does that make sense? I hope. To juxtapose that, if we do the coupon last, that would be f of g of x. So let's go ahead and see how these differ and see which one's a better deal, and see how we could use the idea of composition functions in shopping to maybe save ourselves a couple $100 one day on a car. G of f of x is going to be g of x minus 5, which in turn is going to be 0.9 times x minus 5, which is going to be 0.9x minus 4.5. So if I apply the coupon first, this is how much it's going to cost. I don't know how much a pizza is. Maybe it's 20 bucks. Maybe it's $13.99. Who knows? But I could plug in to X, whatever the price of the pizza is. If I do the other one, f of g of x, that's going to be f of 0.9x. So that means I'm going to take 0.9x and subtract 5 from it. So this is the expression there. So the question is, how much cheaper is it? Can you see from that how much cheaper it is? It's not much, but it's still enough to make a phone call and call somebody who cares. It's enough to go to a concert and watch that one rapper, 50 Cent. Right? 50 Cent. Here's your answer. 50 Cent. Say 50 cents. Big deal, 50 cents. Well, it is a big deal. What if you're going to the car wash and you just got to spray that bird poop off your car? And it's $1.50 to activate the machine. And all you got is $1 in your visor. There's that extra 50 cents. There you go. You get to watch the bird poop off your car because you can do some math. Any questions, comments, concerns, short debates, long debates? It's been real. It's been fun. I hope it's been educational. Have a great day. See you.
Good.